Have you ever just looked up at a skyscraper or maybe driven across some massive bridge and just thought, how? I mean, really, how is all of that stuff just hanging up there, defying gravity? It's a question we kind of take for granted, but behind it, well, that's where we find a fascinating story about science and a constant, invisible battle with the forces of nature.
Okay, just look at these things. These are the Marina City Towers in Chicago. People call them the Corncob Towers, and you can see why. They almost look like they shouldn't be real, and yet, for more than 60 years, they've been standing there, taking on the Chicago wind, their own incredible weight, everything. They're proof of this invisible science that's holding our entire world together.
So that really is the big question, isn't it? How do they stay up? Well, it's not magic, and it is definitely not just good luck. The answer is a field of engineering called structural analysis. You can think of it as the secret science of predicting the future, or at least the future of a building in the middle of a hurricane.
All right, so here's our roadmap. First, we're going to look at the basic reason things stay up at all. Then we'll meet the invisible enemies that are always trying to knock them down. We'll get into the science of stability, peek inside an engineer's toolkit, and then we'll jump in a time machine to see how we got from ancient guesswork to modern supercomputers. It's all about designing a safer world. Okay, first things first. We have to completely reframe how we think about buildings. You see, they're not just sitting there. They are in a constant, silent fight.
Yup, you heard that right, a fight for survival. From the second it's finished, every single structure is being pushed, pulled, twisted, and shaken by all these different forces. And the whole job of a structural engineer, it's to design a champion that can take every single hit and just keep on standing.
So, if our structures are the heroes in this story, who are the villains? Well, in the world of engineering, they have a really simple name for them: loads. A load is basically any force that a structure has to deal with. Think of it as the weight of the world, literally. Every single part of a building is a load. The steel, the concrete, the windows, even the weight of the paint on the walls has to be calculated. Seriously.
Now, check out the contrast here. On the left, you've got this beautiful Gothic cathedral. For centuries, it's just been dealing with its own weight, a predictable force engineers call a dead load. But on the right, that's the aftermath of an earthquake, a sudden, violent environmental load. And for crazy, unpredictable forces like that, you can't just design for strength. You have to design for flexibility, so a building can sway and bend instead of just shattering. The stakes couldn't be higher.
So, on top of the dead load, the building's own weight, engineers have to figure out the live loads. That's us. People walking around, cars driving over a bridge, even your furniture. Then you get the environmental loads. Heavy snow might not seem like a big deal, but just 1 cubic foot of wet snow can weigh over 20 pounds. Now imagine that covering an entire football stadium. And that's before we even talk about wind or earthquakes. You have to be ready for all of it. Okay, so we've met the villains, all these relentless loads trying to tear things down. So how do we fight back? Well, this is where our hero finally enters the scene: structural analysis.
At its heart, structural analysis is like a crystal ball made of math. It uses physics and calculations to predict exactly how a structure is going to behave under all those loads we just mentioned. It lets an engineer see a bridge bend in the wind before a single piece of steel is ever ordered. And this isn't some quick, back-of-the-napkin guess. It's a super detailed process that goes round and round. You can see it in this flowchart. Engineers come up with a design, they estimate the loads, they run the analysis, and then they hit that big question in the middle: is it safe? And if the answer is no, it's right back to the drawing board. And that loop right there, that's the heart and soul of the whole thing. It's this perfect cycle of creativity and caution. An engineer can dream up the most amazing, innovative idea, but this process makes sure that every wild design is absolutely, fundamentally safe before it ever gets built. So, how do engineers actually get the job done? What's in their toolkit? Well, a lot of it comes down to a few surprisingly simple but incredibly powerful geometric shapes. Let's start with the king of shapes, the triangle. It's just naturally the most stable, rigid shape there is. So when you connect a whole bunch of them together, like in a truss, you get something that is ridiculously strong without having to be super heavy. It's why you see them everywhere, from giant bridges to the rafters in your own attic. But for something like a skyscraper, you need a different tool. This is a frame. Now, unlike a truss, a frame has these super rigid, strong connections that can resist bending. They're basically the skeletons of our buildings. And that's just one more tool. Engineers also use arches, suspension cables, thin shells, all these different forms to shape our world.
Now, we've known that shapes like arches and triangles are strong for a long, long time. But our ability to actually analyze them, to do the math, that has gone through an unbelievable revolution. For thousands of years, building was pretty much just trial and error, and a lot of error. The builders of the great cathedrals, they relied on know-how passed down for generations. Then, in the 1800s, it started to become a real science. The first big leap for skyscrapers came in 1924 with a painstaking by-hand calculation method. It worked, but then everything changed.
The computer? I mean, it's hard to even wrap your head around the difference. We're talking about a calculation that would have taken a whole team of engineers weeks of nonstop work with slide rules. Today, a computer program can run an even more complex analysis on the entire building in less than a minute. That colossal leap in power is what unlocked the door to the crazy gravity-defying buildings we see all around us today.
So we've gone through all this complex math, all this history, but why does it actually matter? Well, because at the end of the day, this isn't some abstract science. It's about people. It's about us.
This quote from Aslam Kasamali, who wrote our source material, really says it all. It's a science and an art, all focused on building safe structures. And that one word, safe, is something we all depend on every single day, most of the time without even thinking about it. Think about it. Every time you walk into an office, drive your car over a bridge, or sit in a crowded stadium, you are putting your absolute trust in the work of a structural engineer. You're trusting their analysis. It's the quiet, hidden science that holds up our entire world. And that really brings us full circle. With the power of modern analysis, we can build things our ancestors would have thought was just straight-up magic. So it leaves you with this one really exciting question. As our materials get stronger and our tools get even more powerful, what impossible-looking structures are we